Welcome to another deep dive.
Yeah.
This one's going deep, I think. For those of you who are into physics and philosophy, all that good stuff. You guys sent in a bunch of research on consciousness, quantum mechanics. I even saw some stuff on cell biology and AI. And going through it all, one name just kept popping up, Boscovich.
Yeah, it's like almost like he's hiding in plain sight, kind of a hidden figure in all this modern science stuff.
Right, so who was this guy? What's the deal with his name popping up everywhere? Like, what fields was he even in?
Okay, so let's go way back to the 1700s. Roger Joseph Boscovich. This guy was like a Jesuit polymath, one of those like super geniuses, worked on physics, astronomy, math. I even saw archaeology. He did a little bit of everything.
Talk about a Renaissance man.
Yeah.
Even though, the Renaissance was a while ago.
Right, haha. And get this, he wasn't just like theorizing in his office or whatever. This guy was out there, in the field, surveying the Papal States. I even read that he gave advice on fixing St. Peter's Basilica, the dome.
Wait, hold on. So this guy's thinking about, like, the universe and what matter is made of, but he's also out there getting his hands dirty fixing a giant dome. That's kind of awesome.
Yeah. It shows how wide-ranging his mind was. Okay, so let's get to his big idea, the thing that really has scientists buzzing these days. You could say Boscovich looked at the universe and saw, well, dots. Basically, he said matter, the stuff everything's made of, it's not this continuous thing. It's made of these tiny, indivisible points.
Wait, so everything is just points. I'm trying to picture like those pointillist paintings. Up close, it's just dots, but if you step back, boom, it's a whole picture.
Exactly. That's a perfect analogy. And here's where it gets even cooler. So Boscovich, he didn't think these points, these dots, they touched each other. He said they interact through forces. But these forces, they could be attractive or repulsive, like push or pull. And that depended on the distance between them.
Okay, so these aren't your average dots. They've got a little bit of a personality, huh? Pushing and pulling, like magnets, Depending on how you hold them, they stick together or push each other away.
Precisely. So imagine this, right? You got a graph. One axis is the distance between these particles. The other axis shows the force between them. Boscovich, he imagined this line on the graph. It would go up and down, crossing zero a bunch of times.
So what were they called again?
Point particles.
Right, point particles. So as these point particles get closer or further apart, the force between them is always changing. Attraction, repulsion, back and forth.
Exactly. And this was a huge deal back then because it totally went against the physics everyone believed, the Newtonian physics. Newton, he talked about forces like gravity, which only pull things together, always attractive. But Boscovich, he was saying something way more complex and dynamic was going on.
No wonder modern scientists are digging back into his work.
Yeah.
He sounds like he was almost predicting stuff like quantum mechanics, where things aren't always so black and white, you know what I mean?
Exactly. So let's jump ahead a couple of centuries and see how these Boscovich points, as you called them, are connected to all these modern scientific mysteries you guys sent us.
Okay, that sounds good. Let's start with consciousness, right? Because that seems like the biggest leap, going from like 18th century physics to, what's going on inside our minds.
It is a fascinating link. So some researchers, they're looking at the idea that consciousness, maybe it's tied to quantum stuff happening in the brain. Specifically in these structures called microtubules.
Microtubules, those are like the tiny little support beams inside neurons, right? I
Yeah.
vaguely remember that from biology class. But what do those have to do with quantum physics?
Right, so the idea is that the way these microtubules are structured, it might be just right for quantum phenomena to happen. And this is where Boscovich's ideas come in.
Okay, I'm starting to see how this connects. So are we saying that those point particles with their whole push and pull thing, they're playing a role inside these microtubules?
Exactly. Some researchers are proposing that how those Boscovich points are arranged and how they interact inside microtubules, that could actually mess with their quantum properties. And maybe, just maybe, that's what leads to consciousness, what we experience as consciousness.
Whoa, okay, so these tiny little points, maybe they're the key to our big thoughts. That's a pretty big idea.
Yeah.
But how does all of this connect to something more, concrete like cell biology? I mean, those are two very different things.
Well, that's another area where Boscovich is making a comeback. You familiar with Gerald Pollack's work? He's doing some really interesting stuff with water, specifically something called exclusion zones. And it's changing how we think about cells.
Exclusion zones. Picture like tiny keep out signs inside our cells. What are they?
Okay, so picture this. You have water inside a cell, right? But the water near the surfaces, the insides of the cell, it's not your regular H2O. It gets all structured, almost like a gel. And in these zones, other stuff, like solutes, they can't get in.
So it's not quite solid, not quite liquid. It's like these exclusion zones are bringing some order to the chaos of a cell.
Exactly. And these zones, they do some crazy things, like separating charges, almost like they can store and move energy around.
That's like our cells are full of tiny little batteries all powered by water. That's wild. So where does Boscovich fit in with all this?
Well, some scientists think that the way those Boscovich points push and pull on each other, those forces, that might be what's shaping these exclusion zones. Like they're guiding the water molecules into this ordered state. It's like an invisible dance choreographer, you know?
Yeah.
Those forces are directing the water molecules within our cells.
Okay, I'm starting to get how a theory from like the 1700s could be important for understanding the microscopic world inside us. But what about something super futuristic, like artificial intelligence? How does that tie back to Boscovich?
That takes us to the work of Anirban Bandyopadhyay. He's been working on something called the nanobrain, which is, well, it's a theoretical brain, an artificial one, and it's built using time crystals.
Okay, time crystals. That sounds like something straight out of like Doctor Who or Star Trek.
Right. So time crystals, they're a pretty new idea in physics. They're these structures that repeat in time instead of space. It's like, think of a crystal, but instead of having a repeating pattern in space, it's always oscillating, changing in time.
Okay, so like a crystal that's constantly buzzing with energy? That's wild. But hold on. How do you make a brain out of these things?
The idea is that if you can arrange these time crystals in the right way in a network, you can make a system that can actually process information. Each crystal is like a little oscillator, and they all talk to each other, interact, and that's how the computation happens.
Okay, I think I'm following. But where does Boscovich fit into all of this?
So some researchers, they think that to understand how these time crystals actually communicate, how they process information, you got to go back to Boscovich, to his point particles and their fluctuating forces. Think of each time crystal as a bunch of those points constantly pushing and pulling on each other in this really complex dance.
So it's like those forces, those Boscovich forces, are the language these time crystals use to talk to each other.
That's a great way to put it. And if we can figure out that language, well, maybe we can figure out how to build a truly intelligent machine. Looks like Boscovich was onto something really fundamental, even if people didn't quite get it back in his day.
It's kind of mind-blowing, you know? A framework from centuries ago, potentially driving the development of futuristic tech. It really makes you wonder what other ideas are out there, ideas that we've forgotten about, that might hold the keys to solving the big scientific puzzles we're facing today.
That's a great question to ponder. But before we go too far down that rabbit hole, maybe we should take a step back and look at Boscovich's legacy, how his theory was received in his own time. I mean, why didn't it take off back then? Why did it kind of fade into obscurity?
Yeah, it's almost like he was ahead of his time, waiting for science to catch up.
That's a great way to put it. You see, back then, Boscovich's theory, it was just so different from how people thought about the universe. Everyone was all about Newtonian mechanics. You know, that idea that the universe is like a giant clock, everything nice and neat, predictable. You got forces like gravity, always pulling things together.
Yeah, Newton's clockwork universe. I remember learning about that. But Boscovich, he was saying something different, right? With his fluctuating forces, pushing and pulling depending on how far apart things are. It's like he messed up the clock.
Exactly. His whole theory just challenged everything people assumed back then. Not just the point particle thing, but the way those particles interacted. Newton said it was all about attraction, things pulling on each other. But Boscovich said, no, 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 there's repulsion too, and it's this back and forth, this constant interplay between them.
So it sounds like scientists back then, maybe they weren't quite ready for such a radical idea.
Well, that's part of it, but also Boscovich's theory, it got pretty complicated, mathematically speaking. It required thinking in a very abstract way, and that wasn't super common back then.
So it was a bit of a double whammy. A challenging idea and some really complex math. But it's interesting how, even though his theory was kind of overlooked for a while, it's making a comeback now.
It's like a seed that was planted way back when, and it's finally starting to sprout.
Yeah, and we've seen how it's influencing research in all these different fields like consciousness, cell biology, even artificial intelligence.
Exactly. It just goes to show you sometimes great ideas just need a little time to, take root.
Speaking of which, let's get back to those modern applications. We talked about consciousness earlier, those microtubules and quantum processes. Can we maybe dig a little deeper into that? I'm really curious about how those fluctuating forces could actually play a role in what we experience as consciousness.
Sure. Have you heard of the theory of orchestrated objective reduction? They call it ORCH or R for short.
Orch or R rings a bell. It has something to do with Roger Penrose, right? The physicist.
Yeah, that's the one. Famous for his work on black holes and general relativity. So, Orchvara basically says that consciousness, it comes from quantum processes happening inside those microtubules we talked about, specifically through something called the collapse of the wave function.
Wave function. That's a quantum mechanics term, right? I'm trying to remember what it means exactly.
Basically, it describes the probability of a particle being in a certain state, and when it collapses, that particle chooses a specific state.
Okay, yeah, it's coming back to me now.
Yeah.
So where does Boscovich fit into this whole wave function collapse thing?
Well, some scientists think that those fluctuating forces between Boscovich's point particles, they might actually influence which quantum states are selected within those microtubules, and ultimately that could lead to the collapse of the wave function, which then, boom, you get consciousness.
So it's like those little Boscovich forces are acting as these tiny switches, controlling the quantum processes that lead to our thoughts and experiences.
Yeah, it's a really interesting hypothesis, and researchers are definitely looking into it. Now, you're probably thinking, this is all pretty theoretical, right? How do we actually test these ideas?
To be honest, I was just about to ask that. It's one thing to talk about Boscovich points and quantum processes, but how do we actually see them at work, especially in something as complex as consciousness?
That's the million-dollar question. It's pushing scientists to develop all sorts of new tools and techniques. One area that's really taking off is the study of biophotons.
Biophotons, those are those super faint light emissions from living organisms, right? What do they have to do with Boscovich?
Well, the idea is that these biophotons might actually be a sign of those quantum phenomena we've been talking about. Maybe they even reflect what those Boscovich point particles are doing within the microtubules.
So like little flashes of light showing us those quantum events happening.
Exactly. It's like we're trying to listen in on the conversation happening at the quantum level inside our brains.
And what about those exclusion zones in water? We were talking about those earlier. How are scientists connecting them to Boscovich's ideas?
Remember those fluctuating forces that can attract or repel? Well, some scientists think those forces could be what's creating those exclusion zones, pushing the water molecules into these structured gel-like
So
areas.
those forces are like little architects shaping the water inside our cells.
Precisely. And it could change how we understand how water behaves in biological systems.
So it seems like Boscovich's legacy is more than just a bunch of theoretical ideas. It's actually sparking new research and potential breakthroughs in all kinds of fields.
That's the beauty of science, right? An idea that seems abstract or forgotten can come back around and inspire new discoveries.
Totally. And speaking of new discoveries, what about that nanobrain we talked about earlier? How are scientists actually trying to build a brain using those time crystals?
It's still very early days, mostly theoretical at this point. But the basic idea is to arrange those time crystals in a network, and each crystal acts like this little oscillator. The tricky part is figuring out how to use those oscillations, how the crystals interact, to actually make computations.
So it's like building a computer out of tiny synchronized clocks.
That's a great way to think about it. And this is where Boscovich comes in, with his ideas about the interactions between those crystals.
Okay, I'm hooked. How do those Boscovich points help us build a brain out of these time crystals?
Imagine each time crystal as a bunch of Boscovich's point particles, constantly pushing and pulling on each other. Those fluctuating forces might be the key to how those crystals communicate and process information. It's like a quantum dance, with those forces calling the steps.
So if we can understand those Boscovich forces, we might be able to crack the code of building a truly intelligent machine.
Exactly. And by understanding those forces, we might unlock even bigger mysteries. They could even be the key to understanding dark matter.
Dark matter. You mean that mysterious stuff that makes up like a huge chunk of the universe, but we can't even see it?
That's the one of the biggest puzzles in cosmology.
But how could Boscovich's theory possibly help us understand something as elusive as dark matter?
Well, some physicists are suggesting that dark matter could be made up of particles that interact through forces similar to the ones Boscovich described.
So those fluctuating forces attracting and repelling, maybe that's what's holding dark matter together.
That's the idea. It's still very speculative, but it's an intriguing possibility. And it shows how Boscovich's work, which started way back in the 1700s, is shaping cutting-edge research today.
It's amazing how an idea that was overlooked for so long could potentially change our understanding of the universe. Makes you wonder what other forgotten gems are hidden away in the history of science, just waiting to be rediscovered.
Absolutely. And that's what makes exploring science so exciting. It's all about discovery, and sometimes the most unexpected paths lead to the most groundbreaking insights.
I totally agree. All right, let's get into those experiments. What are scientists actually doing to test out Boscovich's ideas?
One area that's really hot right now is looking at biophotons in photosynthesis. You know how plants use sunlight to make energy?
Yeah, photosynthesis, pretty basic stuff, right? Like one of the things that makes life on Earth possible.
Exactly. But it turns out there's more to it than we thought. So during photosynthesis, plants, they actually give off these super weak photons, these biophotons. And some scientists think these biophotons, they might be part of how energy gets moved around between molecules.
So it's not just about absorbing light, it's also about giving off light as part of the whole energy process.
Right. And here's where Boscovich comes in. Some researchers think his idea about those point particles and their forces, that might explain how that energy transfer happens at the quantum level.
So those tiny Boscovich forces are like orchestrating this whole dance of light and energy inside plants.
It's a pretty elegant idea, right? And if we can really understand it, well, think about it. It could totally change how we develop solar energy technology. Imagine if we could harness the power of photosynthesis, but on a massive scale.
That would be a game changer. And it all goes back to a theory from the 1700s. Amazing. Are there any other experiments, actually putting Boscovich's legacy to the test?
Oh yeah, definitely. Scientists are also looking at his ideas in materials science. Traditionally that field, it's been all about the structure of materials, how the atoms are arranged to give them certain properties. But Boscovich's theory, with all its talk about forces, it opens up a whole new way of thinking about materials.
So instead of just looking at how atoms are arranged, we're thinking about those Boscovich forces that are always acting between them.
Exactly. And if we understand how those forces work, maybe we can make materials with totally new properties, things we haven't even imagined yet.
Like what? Give me an example. What kind of new properties are we talking about?
Well, some researchers are looking at using Boscovich's ideas to design self-healing materials.
Self-healing materials. Okay, now that sounds like science fiction. How would that even work?
The idea is to make materials that can actually repair themselves when they get damaged. Imagine your car gets a dent and it just fixes itself. Or a bridge with a crack that just heals up.
That would be incredible. But seriously, how is that even possible?
So the idea is you design the material with special structures or molecules, and they respond to those Boscovich forces, those fluctuating forces. So when the material gets damaged, those forces cause it to reconfigure itself and close up the damage.
So those forces, they're not just theoretical anymore. They could actually be used to design real-world materials. What else? What other cool things are people working on?
Well, there's also work on materials that can change their properties on demand. Imagine clothes that adapt to the temperature, or windows that can control how much light comes through, or even electronics that can change what they do depending on what you need.
It's like we're on the verge of a materials revolution. And it's all thanks to a theory that was basically forgotten for, 200 years?
It really shows you how science works. It's not always a straight line. Sometimes an idea just needs time to, I don't know, maybe simmer for a bit, to be rediscovered and seen in a new light.
It makes you appreciate how everything in science is connected, right? And how it's important to go back and look at those old theories, even the ones that people have forgotten about. Who knows what other amazing ideas are out there just waiting for someone to rediscover them?
I think that's a great point to end on. And it's what makes science so exciting. It's a journey of discovery, and you never know what you're going to find around the next corner.
I couldn't agree more. Well, we've covered a lot of ground today, haven't we? From consciousness to the future of material science. It's amazing how Boscovich's ideas have connected everything together.
His theory might have come from the 1700s, but it's proving to be incredibly relevant to the science of the 21st century.
It really shows you that sometimes the most important discoveries come from taking a fresh look at those old, forgotten ideas. And who knows, maybe out there somewhere, there's another Boscovich waiting to be rediscovered, someone who will inspire a whole new generation of scientists and thinkers.
And I think that's the biggest takeaway from our deep dive today. Stay curious, Be open to new possibilities and never underestimate the power of an idea, no matter how old or unusual it might seem.
Couldn't have said it better myself.
Yeah.
A huge thank you to our expert for guiding us through the fascinating world of Boscovich. And to our listeners, we encourage you to keep exploring, keep digging into those forgotten corners of scientific history. You never know what incredible ideas you might uncover.